So in this lesson, we'll want to consider appropriate mechanisms that we can have in place for other data hazards, picking up where we left off. So one consideration that we want to take into account is what exactly if we can't restructure our program or change the order of appropriate instructions. So one thing to consider is what hardware mechanisms can we put in place to help reduce or eliminate appropriate bubbles or no-op instructions in our data path. And so one option that we can make use of is called a read pending signal. And this would be an additional bit that we add to our register file. And so this will allow for the IDRR stage to set the bit in the register if it wants to read. And so once it's set, the other stages in our pipeline, execute, memory, and WB, can generate a new value that gets supplied to the ID and RR stage. So this can introduce a little bit more complexity in terms of hardware, but it allows for a reduction in possible bubbles within our data path. And so once the instruction reaches the WB stage, the bit is cleared. And so our essential logic that we could analyze for this, let's consider that we have two instructions, I1 and I2, in which operation is stored into R1, but R1 is also needed for I2. So in this example, we can say that the ID RR stage will set the value of RP to equal to 1, and so the forwarded value is set. If it's not set, then we're going to read from our entry from our dual ported register file. And so let's consider how this might affect the number of bubbles that would be introduced for an example for a read after write. In this case, we see that if we do not have unrelated instructions in place, then it's going to introduce at least 3 bubbles without forwarding. If we have instructions that can be put in between B1 and B2, then this will introduce, we only have 2 bubbles without forwarding. If we have 2 instructions added in between I1 and I2, then we have 1 bubble, and 3 or more instructions will mean that we don't have any bubbles that are in our data path. So what exactly happens if we do have an instruction that intervenes? In this case, now all we need to do is forward our data path. We need to forward from memory to IDRR for instruction 3. If we have 2 instructions that intervene, then we just need to forward from the write back to our IDRR stage. And so let's consider if we're going to need to load a word. And so a load instruction allows for essentially a special case, and that we'll need to, even with the data forwarding, we have to insert a bubble. And so in this case, we have I2 is immediately following I1. But we won't have a value for R1 until the end of the memory cycle. So in order to, we'll have to introduce a delay of 1 cycle that leads to 1 bubble that we have. And so this is because we won't get the data until I2 gets to memory. And so let's consider how a load word will make changes to the number of bubbles that are introduced with forwarding. And so with the load instruction here, we see even when there's no unrelated instructions, then it's going to introduce one bubble into our data path. And so how exactly does our generalized register forwarding look in our data path? We're going to need to introduce some additional data lines that would occur at all stages. And so we'll have to introduce data lines for execute, memory, and write back at each stage. And then we also have to take into consideration that we have 2 registers that need to be fed as well. And so how would we implement this? And so this provides a generalized example. We'll need to take into consideration that we'll need multiplexers for both A and B. And at the IDRR stage, this is going to put the register numbers that are used for A and B onto the 2 forwarding register buses. For each stage we see here, we'll need to have the other stages to be able to compare any of the results for their destination register with the register numbers on the 2 register buses. We'll have to make sure that we take into consideration that if the destination register matches a register on a register forwarding bus, then the stage opens the driver to allow the destination value it has, and that will be put onto the appropriate A or B forwarding data bus. And so our IDRR stage gets a signal that a match has been found on either the A or B operand via either the read pending A or read pending B. And so once the read pending A or read pending B signals are sent, then we can make use of appropriate multiplexers in the IDRR stage. And this will allow for the data from A or B forwarding data bus lines to be selected instead of the register file. And so let's consider what might be needed if we're going to implement this solution. And without including all of the control and data forwarding lines, we have our appropriate representation with our multiplexers. The program counter is represented. We'll have a logical unit for each stage that needs to occur. We have our dual ported register file, as well as appropriate inputs for the multiplexers into our ALU during our execution stage. And so it's also important to consider that we have other data hazards to consider, such as write after read. This doesn't necessarily present much of a problem since we've already read the registers for instruction 1 into our debuffer before I2 gets started. And then we also have write after write data hazards that could occur. And so this will result in a stall for I2 by instruction 1 as well. And so if we want to consider the different type of hazards that are in place, let's say we take a look at 3 instructions that we have. So we can't let I2 move forward until I1 is retired from the pipeline. So this can present a read after write hazard. Otherwise, I3 could get the wrong value from I1 instead of I2. And then we can also have write after write hazards occurring for I1 and I2 as well with regards to R1. And so now we can also consider other instructions that might occur and what type of hazards that they might propose. And in this case, we can focus our attention on the branch if equal to and a control hazard that would be introduced during our data path. And this is a problem because we don't know what the instruction is in the fetch stage until we execute the branch of equal. And so now let's kind of consider what we need to do in order to handle the BEQ instruction. And so conservative handling of branches say that we should wait until the branch outcome is known. And that means that we'll need to essentially stall the pipeline and send the number of no ops from the instruction fetch state. Once we have the branch outcome, we can resume normal execution. And we'll need to do a comparison to see whether we're going to take the branch or not. So the result of the comparison is if it's known if there is a need to branch, then the program counter gets the target address of the branch. And so we have 2 cases that we need to consider in this regard. If the branch is taken or the branch is not taken. So let's take a look and see what happens in our pipeline for each one of our cases. So the instruction fetch stage doesn't quite know yet if we're going to need a branch. And so our instruction will continue on into the IDRR stage, but still at this point, we don't have a value, so we don't know what to do. And so IDRR tells our instruction fetch stage to stall, and that's when a no-op instruction gets inserted. In cycle 3, we're going to execute our branch of equal to operation. And so that is calculated and there isn't a difference, so our branch is going to be taken. We issue a stay, and PCN plus offset is being calculated here. And so that value gets stored into our program counter at the end of our execution stage. And so then BEQ continues down our pipeline to memory. At this point, we've had 2 no-ops that have been introduced, but our instruction fetch stage is able to retrieve the next instruction, and we'll call this just instruction T. But we still have our 2 bubbles in the pipeline. And now our branch of equal to advances to our write back stage. And so in this regard, we have that if the branch is taken, we're going to still have 2 bubbles that are introduced. Now let's consider our other case if the branch is not taken. So A minus B is calculated and it's a non-zero value. So our branch is not taken, but we do need to introduce a one no-op instruction. The program counter is already pointing to our current sequential path. So we continue down our normal pipeline execution. And so in this case, the benefit that we have if the branch is not taken is that we have 1 pipeline bubble that has been introduced. And so at a high level, that provides us with an understanding of how branch instruction is handled and handled with in a conservative manner. So let's consider with the conservative handle of branches, how many bubbles will there be at a minimum? Will it be 1, 2, 3, or 0 bubbles? And so we just saw in our previous example that if the branch is not taken, then at the most we will introduce at least 1 bubble. So the keyword you want to focus on is at least, and in this case we have 1 bubble that will be introduced into the pipeline. And then on the other hand, we want to consider how many bubbles will be introduced into the pipeline at most. And we saw that if the branch is taken, then at most it's going to introduce 2 bubbles into the pipeline. And so let's consider that we have the following code and we want to illustrate each stage in our pipeline. So we have our BEQ, we have an add, we have a load, and then we have a NAND instruction as well. And so in a perfect world, our pipeline would execute and complete within 8 cycles. But this is not going to be the case, of course. And so this is going to result in a stall starting with our BEQ instruction. And this is going to be because only at the end of the execute stage is when we'll know what to do with our BEQ instruction. So what needs to happen for cycle 2? IDRR is going to tell the instruction fetch to stall after fetching. So instruction fetch will send a no-op to IDRR at the end of the cycle. So instruction fetch then sends another no-op into the ID RR at cycle 3. During the execute stage for our first instruction, we set the PC, the execute sets the PC, and that gets saved to our FBUF plus the offset. So NAND is then fetched. And so only once we reach the end of the execute stage do we know if, or do we know what the target address for the branch instruction will be. And so in this case, we've introduced 2 no-ops into the pipeline. So finally, instead of getting to completing in 8 cycles, we're completing in 9 cycles. Now, let's consider if the branch is not taken in our pipeline. With this regard, we finish with our stalls in cycle 8. And so with the calculating the cycle per instruction difference, if we consider whether the branch is taken or if it's not, we see that if the branch is taken for our instructions, we have a total of 9 cycles, 3 instructions. And so our CPI, average CPI, is going to be 3. If the branch is not taken, then our average CPI is going to be 2.66. So this introduces some good questions of what are the best ways that we can handle improving branches and how they're handled. And this will be the focus for our next lesson.